Science thrives on reproducibility. An experiment conducted in Tokyo should yield the same results when replicated in Toronto. A measurement taken on Tuesday should match one taken on Thursday. The scientific method has a dirty secret. It doesn't work well with unrepeatable observations. This repeatability is the foundation of scientific knowledge, the bedrock upon which we build our understanding of reality. But what happens when you can't repeat the observation? When the experiment occurs once, 40 million kilometers away, and then never again? This is the problem with Venera 13. The lander operated for 127 minutes and then died. Its electronics fried. Its systems crushed and corroded. No human has examined the landing site since March 1st, 1982. No subsequent mission has visited that location. The 8 photographs it transmitted represent the entirety of our ground-level visual data from that precise spot on Venus. They're all we have, and they're all we may ever have. In this epistemological void, interpretation becomes everything. And interpretations, as it turns out, vary wildly. Dr. Vladimir Krasnopolsky spent 15 years analyzing atmospheric data from the Venera missions at the Russian Academy of Sciences before emigrating to the United States in 1992. Now, in his 80s and retired from NASA's Goddard Space Flight Center, he speaks with the careful precision of someone who has watched colleagues ruin their reputations by speculating too freely. The images are ambiguous, he says, choosing his words carefully. Resolution is approximately 1 millimeter per pixel at the closest range, degrading to several millimeters at distance. At this resolution, many geological features can appear artificial. The human brain is designed to find patterns. It's how we recognize faces, track prey, avoid predators. But this same capability leads us to see organization, where only randomness exists. He pulls up the famous image 3 from Venera 13 on his computer. The photograph that has caused so much controversy. Even on a modern high-resolution monitor, the scan lines are visible. The image grainy and orange-tinted. He zooms in on a cluster of rocks that several researchers have identified as anomalous. Look here. He points to a roughly disc-shaped object. Some colleagues claim this shows too much symmetry to be natural. But basaltic rocks often fracture in columnar patterns, creating cross-sections that appear circular. Without being able to examine it directly, we cannot determine if this is unusual or perfectly ordinary. He clicks to another section of the image. And here, these objects that some say appear organized. But think about terrestrial lava flows. They create patterns, pressure ridges, tumuli, hornitos. From limited perspectives, these can seem artificially arranged. We're looking at one snapshot from one angle under alien lighting conditions. Our interpretations tell us more about ourselves than about Venus. Krasnopolsky represents the conservative mainstream of planetary science, the community that has largely dismissed the anomalies as misinterpretation. But his arguments, while reasonable, don't fully account for all the observations, and he knows it. The apparent movement between frames, that's more difficult to explain, he admits. The telemetry shows the lander remained stable. The camera calibrations were consistent, but equipment was operating far beyond its design specifications. Extreme temperature differentials could cause optical distortions we didn't anticipate, or perhaps small debris falling from the lander itself, though we see no evidence of this in the images. He pauses, considers his next words carefully. I don't believe we photographed life on Venus. but I do believe we don't fully understand what we photographed. And that's a different kind of problem. The problem becomes clearer when you examine what else the Venera landers detected. Data that received far less attention than the photographs, but maybe equally puzzling. Venera 9, 10, 13, and 14 all carried nephelometers, instruments designed to detect aerosols and particles in the atmosphere. During descent, these instruments registered expected readings: sulfuric acid droplets, fine dust, the characteristic composition of Venus's cloud layers. But at the surface, several of the landers detected something unexpected: variations in atmospheric opacity that couldn't be explained by wind or weather patterns. The variations were subtle, brief fluctuations in the amount of particulate matter near the ground. On Earth, such variations would be unremarkable. Dust gets kicked up. Settling patterns change with air movement. Biological activity stirs sediments. But on Venus, with wind speeds at the surface measuring less than 1 meter per second and no obvious mechanism for disturbing settled material, these fluctuations were anomalous. Dr. James Garvin, chief scientist at NASA's Goddard Space Flight Center, has spent years analyzing orbital data from Venus and comparing it with surface observations. He's particularly interested in what he calls transient surface phenomena, changes detected by orbiters that suggest something on the surface is not static. We've observed variations in infrared emissions from certain regions, Garvin explains. These could indicate volcanic activity, which we know occurs on Venus. But some variations don't match volcanic patterns. They're too localized, too brief, too irregular. They appear almost random, but with a periodicity that suggests some underlying process. He brings up radar maps of the Venusian surface, compiled from the Magellan mission that orbited Venus from 1990 to 1994. The maps show a complex landscape of volcanic features, impact craters, and vast plains. Magellan gave us incredible global coverage, resolving features down to about 100 meters. But here's the thing. When we compare Magellan's maps to earlier radar data from Venera 15 and 16, we see changes. The changes are subtle, features that appear brighter or darker in radar returns, suggesting alterations in surface roughness or composition. Most can be explained by volcanic activity. Venus is geologically active, with evidence of eruptions occurring within the last few million years, possibly within the last few thousand. But not all changes fit volcanic models. There are regions where radar reflectivity has changed without any obvious volcanic explanation, Garvin continues. No lava flows, no ash deposits, no thermal signatures that would indicate recent eruptions, just changes in how the surface reflects radar, as if something is modifying the texture or composition of the terrain. He's careful not to speculate about what that something might be. In planetary science, suggesting biological explanations without overwhelming evidence is career suicide. But he's equally careful not to dismiss the observations as meaningless. Venus is the least understood terrestrial planet, he states flatly. We have better maps of Mars, better surface data from Mars, better atmospheric models for Mars. We've sent dozens of missions to Mars and exactly 0 surface missions to Venus in the last 40 years. Our ignorance about Venus is profound. And that ignorance creates a space where mysteries can hide. One mystery that can't hide is the phosphine detection of 2020. The announcement came in September of that year. Published in Nature Astronomy by a team led by Professor Jane Greaves of Cardiff University. Using the James Clerk Maxwell Telescope in Hawaii and the ALMA array in Chile, they detected spectral signatures consistent with phosphine gas in Venus's atmosphere at altitudes around 55 kilometers above the surface. The detection was significant because phosphine, a molecule consisting of one phosphorus atom bonded to 3 hydrogen atoms, shouldn't exist in Venus's atmosphere. The compound is thermodynamically unstable under Venusian conditions, requiring continuous production to maintain detectable levels. On Earth, phosphine is produced by anaerobic bacteria, by industrial processes, or by decomposition of organic matter. On Venus, none of these sources should exist. The reaction from the scientific community was immediate and intense. Some researchers celebrated it as possible evidence of aerial life, microorganisms floating in Venus's cloud layers, where temperatures and pressures are far more benign than at the surface. Others attacked the methodology, questioning whether the spectral signatures really indicated phosphine or might be explained by other molecules. What followed was a masterclass in scientific controversy. Multiple teams reanalyzed the data, reaching different conclusions. Some confirmed the detection. Others claimed the signals were artifacts or misidentifications. Additional observations from other telescopes yielded conflicting results. Papers were published, retracted, revised. Careers became invested in being right. Dr. Sanjay Limay, a planetary scientist at the University of Wisconsin-Madison, has studied Venus's atmosphere for 4 decades. He takes a measured view of the phosphine controversy. The detection was at the edge of instrumental sensitivity, he explains. Such detections are always problematic. Small calibration errors, unexpected interference, processing artifacts, any of these can create false signals. But the counter-argument is equally important. Absence of evidence is not evidence of absence. If phosphine exists at lower concentrations than our instruments can reliably detect, we wouldn't find it even if we looked. He pivots to a related observation that has received less attention: the dark UV patches in Venus's clouds. Orbital observations of Venus in ultraviolet wavelengths reveal dark regions in the upper cloud layers that absorb UV radiation strongly. These patches change over time, appearing and disappearing on cycles of days to weeks. Their composition remains uncertain. Proposed explanations include sulfur compounds, iron chloride, or various allotropes of sulfur. But none of these proposals fully match the observed spectral properties. One hypothesis that keeps resurfacing, Limay says carefully, is that the UV absorbers are biological. Microorganisms containing pigments that protect against UV radiation. Similar to how terrestrial bacteria produce carotenoids or melanin, the patches would represent blooms, populations growing and dispersing in the cloud layers. He anticipates the obvious objection. Yes, the environment is extremely acidic. Sulfuric acid clouds that would dissolve any terrestrial organism immediately. But life adapts. We've found bacteria on Earth that thrive at pH 0, that actually require acidic conditions. Is pH -1 or -2, which we estimate for Venus's clouds, really an absolute barrier? Or just beyond what we've encountered so far? The question is rhetorical, but it points to a deeper issue: the limitations of our imagination when conceiving of alien life. Every organism we've ever studied shares fundamental biochemistry, DNA or RNA encoding genetic information, proteins performing cellular functions, lipid membranes creating compartments. This universality suggests these solutions are optimal, perhaps inevitable, but it also means we lack examples of truly alien biochemistry. We don't know what else is possible. Venus might be showing us what else is possible. Or it might be showing us elaborate geological and atmospheric processes that superficially mimic biological patterns. Distinguishing between these possibilities requires better data, and better data requires new missions. Several are planned. NASA's Da Vinci mission, scheduled for launch in the early 2030s, will drop a probe through Venus's atmosphere, analyzing composition in detail and taking high-resolution photographs during descent. Gakuseiki won't land. The probe is designed to survive only until impact, but it will provide the first new atmospheric data in decades. ESA's Envision orbiter, launching around the same time, will use radar and spectrometers to map the surface and study geological activity. It will search for active volcanism, measure outgassing, and track changes over time. India's Shukrayan-1 mission aims to study the atmosphere and surface from orbit, with particular attention to understanding what happened to Venus's water. Every model of planetary formation suggests Venus should have had oceans early in its history, perhaps for hundreds of millions of years. Where did that water go? Was it lost to space gradually, or did some catastrophic event strip it away? These missions are important, but they're all orbiters or atmospheric probes. None will land. None will return to the surface where Venera 13 took those 8 photographs. None will examine the rocks that might or might not be arranged in patterns. The reason is simple: cost and risk. Landing on Venus is extraordinarily difficult, requiring technology that must function in conditions that destroy conventional electronics within hours. The engineering challenges are solvable. The Soviets proved that. But the solutions are expensive, and mission planners must justify costs against scientific return. The argument against Venus surface missions goes like this. We already know Venus is a hellish wasteland. Orbital data can tell us about atmospheric composition, global geology, and climate history without the risk and expense of landing. The money would be better spent on Mars, where conditions are more amenable and the potential for discovering past or present life is higher. Venus is scientifically interesting, but not scientifically compelling. This argument would be more convincing if we actually understood what the Venera landers found. Professor Kevin Baines, a senior research scientist at NASA's Jet Propulsion Laboratory, has developed instruments that have flown on missions to Venus, Jupiter, and Saturn. He's analyzed data from every Venus mission ever flown and has strong opinions about our current approach to the planet. We're making a category error, he argues. We're treating Venus as a solved problem when it's actually a profound mystery. Yes, we know the bulk atmospheric composition. Yes, we know surface temperature and pressure. But we don't know why Venus evolved so differently from Earth. We don't know what's happening at the surface right now. We don't know if there are active geological processes that could support chemosynthetic life. We don't know if the atmosphere hosts organisms. We know almost nothing. He becomes more animated as he continues. Consider what we don't know. Is there current volcanism? We think so, but can't confirm it. Are there plate tectonics? Probably not, but we're not sure. What's the composition of surface rocks in different regions? We have data from only 4 landing sites out of an entire planet. What causes the dark UV patches? Unknown. What's maintaining the sulfur dioxide levels in the upper atmosphere? Unclear. Why does the superrotation of the atmosphere, winds moving at 400 kilometers per hour at cloud top level, even exist? We have models, but no consensus. The list goes on. Venus rotates backwards relative to most planets, spinning once every 243 Earth days. This retrograde rotation is slower than Venus's orbital period of 225 Earth days, meaning a Venusian day is longer than a Venusian year. Why? The most popular hypothesis involves a massive impact early in the planet's history. But this raises questions about how Venus retained such a thick atmosphere after such an event. The planet has relatively few impact craters, around 1,000, compared to hundreds of thousands on the Moon or Mars. This suggests the surface is young, perhaps 300 to 600 million years old. But young by what mechanism? Did Venus undergo global resurfacing, where volcanic activity covered the entire planet? If so, what triggered it? And could it happen again? These aren't merely academic questions. Understanding Venus is crucial to understanding Earth's past and future. Both planets formed from the same material, at similar distances from the same star. Both likely started with similar atmospheres and surface water. Yet Earth developed oceans, life, and a stable climate, while Venus became a superheated wasteland. What was the fork in the road? What different path did Venus take? And crucially, could Earth take that same path? The answer matters because Earth is warming. Human activities are increasing atmospheric carbon dioxide from 280 parts per million in pre-industrial times to over 420 parts per million today, heading rapidly toward 500. This increase is changing our climate, melting ice caps, acidifying oceans, and altering weather patterns. The changes are real, measurable, and accelerating. Venus shows us what runaway greenhouse warming looks like at its extreme. The planet's surface temperature is 475 degrees Celsius, not because it's close to the sun. Mercury, closer still, has a lower average temperature. Venus is hot because its thick carbon dioxide atmosphere traps heat with extraordinary efficiency. The question isn't whether Earth will become Venus. It's how much warming we can tolerate before triggering feedback loops that become self-sustaining. Could increased atmospheric water vapor from warming oceans trap more heat, leading to more evaporation, creating a feedback loop? Could melting permafrost release enough methane, a far more potent greenhouse gas than carbon dioxide, to accelerate warming beyond our control? Could changes in ocean circulation or atmospheric patterns trigger tipping points that transform Earth's climate into something unrecognizable? Venus tells us these scenarios aren't science fiction. They're real possibilities that have actually occurred on a terrestrial planet. Venus is our cautionary tale, our glimpse into a possible future if we mismanage our own atmosphere. But to learn from Venus, we need to understand Venus, and that requires going back. Dr. Martha Gilmore, a planetary geologist at Wesleyan University, is a principal investigator on the Veritas mission concept. NASA has considered it multiple times, but never fully funded it. Veritas would map Venus with unprecedented resolution, revealing surface features down to 15 meters across. It would also carry a spectrometer capable of determining mineralogy from orbit, allowing scientists to understand surface composition across the entire planet, not just at 4 landing sites. We need global context, Gilmore emphasizes. The Venera landings were heroic achievements, but they sampled 4 points on an entire world. Imagine if our only knowledge of Earth came from 4 locations, say Hawaii, Iceland, the Sahara, and Antarctica. What kind of picture would we have? We'd miss continents, oceans, forests, cities. We'd have data points, but no understanding of the whole. She pulls up a map showing the Venera landing sites, Venera 9 and 10 in the Beta Regio Highlands, Venera 13 and 14 on the edge of Navka Planitia. These sites were chosen for engineering reasons, relatively flat terrain that minimized landing risks. But they might not be representative. What if the interesting geology is elsewhere? What if the anomalous features are localized to specific regions? This is the fundamental problem. We're trying to solve a planetary mystery with data from 4 locations, sampled decades ago by instruments that survived less than 2 hours each. It's like reconstructing a novel from 4 random sentences. Yet within those 4 sentences, there are suggestions of a larger story. The chemical composition data from Venera 13 and 14 showed rocks similar to Earth's volcanic formations, but with subtle differences in alkali content. The nephelometer readings suggested atmospheric dynamics we don't understand. The photographs showed features that might be ordinary or might be extraordinary. And then there's what the landers heard. Each Venera lander carried a microphone, a simple device intended to measure wind speed by detecting acoustic noise. At the surface, they recorded sound, the first audio ever captured on another planet. The recordings reveal a quiet world. With such a dense atmosphere, sound behaves differently than on Earth, traveling more slowly and attenuating rapidly. But embedded in the recordings are sounds that have never been satisfactorily explained. Brief, irregular acoustic events that don't match wind noise or equipment sounds. The Soviets classified these as microseisms, tiny ground vibrations from geological activity. But their distribution and characteristics don't quite fit seismic models. Dr. Alexei Koroshev is one of the last surviving members of the original Venera acoustics team, now in his 90s and living in St. Petersburg. He remembers his first reaction to the recordings. "We heard something alive," he says in Russian through a translator. Not alive in the biological sense, perhaps, but dynamic. Venus was speaking to us, and we didn't understand the language. He clarifies. The sounds could be natural, almost certainly are natural. Rock settling, gas releases, thermal cracking, but their pattern, the way they occurred in clusters, with gaps, then more clusters. This suggested some kind of process, regular but not periodic, organized but not mechanical. Koroshev has lived with these recordings for 4 decades, listening to them repeatedly, analyzing them with increasingly sophisticated software. He's published his findings in Russian journals that few Western scientists read. His conclusions are tentative but provocative. The acoustic events correlate with the moments when the lander's cameras captured images showing possible movement of surface objects. I'm not claiming causation, he's careful to note. Correlation is not causation, but the timing is suggestive. When objects appeared to move in photographs, we detected acoustic events. This could mean the objects were actually moving, making sound as they did. Or it could mean ground vibrations were causing both the acoustic events and camera artifacts that looked like movement. Or it could be pure coincidence. We took so little data that statistical significance is impossible to establish. He pauses, then adds, "But in my heart, as an old man who will not live to see Venus missions answer these questions, I believe we detected something real. Something happening on the surface that we witnessed but did not understand. Whether geological or biological, or something we have no category for? I don't know. But real. This is where the mystery stands. We have observations that might be meaningful or might be artifacts. We have data that could indicate unknown processes or could result from instrument errors. We have patterns that might reveal something profound about Venus or might reveal only the human tendency to find patterns where none exist. The scientific method demands we remain skeptical, that we default to the simplest explanation, that we don't multiply entities beyond necessity. These principles are sound. They've served science well for centuries, protecting us from seeing what we wish to see rather than what actually exists. But science also demands we follow evidence where it leads, even when it leads toward uncomfortable possibilities. And the evidence from Venus, fragmentary, ambiguous, frustratingly incomplete, refuses to point clearly in any direction. What the Soviets found on Venus remains, after all these years, genuinely unknown. Not unknown because we haven't looked, but unknown because we looked once, briefly, and what we saw doesn't fit comfortably into our existing frameworks. The photographs show rocks. The sensors detected variations. The microphones recorded sounds. These are facts. But what those facts mean? That's interpretation. And interpretation requires context we don't have. The only solution is to return, to look again with better instruments, to stay longer, to see more. Until we do, Venus keeps its secrets, and the mystery deepens with every year that passes. Every mission we don't fund. Every question we don't pursue. In Moscow, in a vault at the Russian Academy of Sciences, the original data tapes from the Venera missions are slowly deteriorating. Magnetic media degrades over time, and the playback equipment is obsolete. Efforts are underway to digitize everything, but it's a race against time. Soon, the raw data, the actual signals sent back from Venus before processing and interpretation, may be lost forever. If that happens, we'll be left only with images and processed data, removed by one more step from the actual observations, and the mystery will become that much harder to solve. The photographs from Venera 13 show rocks on an alien world, but increasingly, they also show the limits of our ability to understand what we observe when we venture into truly alien environments. And those limits, perhaps, are the real discovery. The real lesson Venus has to teach us about the cosmos and our place in it. The silence in the control room was deliberate. Not the silence of absence, but of concentration. 30 engineers and scientists watched telemetry scroll across monitors. They were tracking a machine descending through an alien atmosphere, 40 million kilometers away. Every data point mattered. Every measurement could be the last. It was March 1st, 1982. Venera 13 was 7 minutes from the surface of Venus. The lander had separated from its orbital carrier 40 minutes earlier. It began its plunge into the atmosphere at 17 kilometers per second. At that speed, friction with the dense carbon dioxide atmosphere generated extreme heat. Temperatures exceeding 3,000 degrees Celsius hit the heat shield. The spacecraft's outer layers ablated away as designed, sacrificing themselves to protect the instruments inside. At an altitude of 64 kilometers, velocity had decreased. Approximately 250 meters per second, the parachute deployed. It was made of material that could withstand sulfuric acid. Venus's cloud layers contained this acid, a cloth that on Earth would dissolve in seconds. But here, it needed to survive long enough. long enough to slow the descent through the most hostile atmospheric environment in the solar system. The engineers had calculated everything with obsessive precision. Too slow a descent. The lander would spend too much time in the hot lower atmosphere, degrading systems before reaching the surface. Too fast. The impact would damage instruments. The optimal descent time from parachute deployment to landing was 63 minutes. They had built the parachute to deliver exactly that. At an altitude of 47 kilometers, atmospheric density increased. Temperature climbed past 200 degrees Celsius. The parachute was jettisoned. It had done its job. From here, the lander would fall freely. Its descent slowed only by atmospheric drag. In the thick, lower atmosphere of Venus, air with the density of water at significant ocean depths, drag was considerable. The telemetry showed everything proceeding nominally. Temperature rising, 300 degrees, 400 degrees. Pressure increasing, 20 bar, 40 bar, 60 bar. The lander's titanium sphere was designed to withstand 95 bar. Safety margins built in. But margins mean little when reality exceeds predictions. Earlier Venera missions had learned this the hard way. At an altitude of 2 kilometers, descent velocity had decreased to 7 meters per second. Impact would be survivable. The instruments would have their chance. 1 kilometer. 500 meters. The radar altimeter provided continuous updates. 200 meters. 100 meters. 50. Contact. The lander hit the surface of Venus and survived. Immediately, the timer started. Not a countdown, but a countdown to failure. Measuring how long the spacecraft could function before the environment destroyed it. Previous landers had lasted 23 minutes, 50 minutes, 65 minutes. Venera 13 was built to survive longer, but how much longer was uncertain. The first task was orientation. The lander had to determine which way was up, deploy its camera booms, begin operations. This took 3 minutes. In that time, the exterior temperature stabilized, 475 degrees Celsius, the pressure at 92 bar, equivalent to being 900 meters underwater on Earth. At 3 minutes and 20 seconds after landing, Venera 13 took its first photograph. The image formed gradually, transmitted in strips. Scan lines built up on monitors in Moscow, revealing an alien landscape, only the 8th time in human history, and the first time in color. The scientists leaned forward, studying the orange-tinted rocks scattered across the surface, the flat horizon barely visible through atmospheric haze, the piece of the lander itself in the foreground, providing scale. But they weren't just looking at rocks. They were looking at 475 degrees, at 92 bar of pressure, at an atmosphere that would kill any terrestrial organism in seconds. They were looking at conditions so extreme that lead would melt. That water couldn't exist in liquid form. That chemical reactions proceeded at rates impossible on Earth. And in those conditions, they were seeing geology. The rocks appeared to be basaltic, volcanic in origin. Their sharp edges suggested recent formation, or at least minimal weathering. On Earth, basalt erodes relatively quickly, through reaction with water, exposure to weather cycles. On Venus, the weathering mechanisms would be entirely different. Reactions with the carbon dioxide atmosphere, thermal stress from the day-night cycle, which took 117 Earth days, possibly chemical alteration by sulfur compounds. But the rocks were there, solid, real, measurable. The landscape wasn't featureless. Venus had topography, geology, a surface that told a story, if you could read it. The second photograph came 21 minutes later, showing a different section of the landscape. The camera had rotated, capturing a panoramic view. More rocks, different arrangements, the same general character. The orange light pervaded everything, a consequence of Rayleigh scattering in the thick atmosphere, which filtered out shorter wavelengths and bathed the surface in amber. At 47 minutes, the drilling mechanism activated. This was the primary scientific objective: to obtain a sample of Venusian soil and analyze its composition. The drill bit rotated slowly. The mechanisms designed to operate at these temperatures couldn't move quickly, without seizing. It pushed into the surface, encountering resistance. The rock wasn't soft volcanic ash, but consolidated material, possibly weathered basalt or compacted sediment. The drill extracted a sample, transferred it to the X-ray fluorescence spectrometer, an instrument that would bombard the material with X-rays and measure the emitted radiation to determine elemental composition. This was delicate work, requiring stable temperatures and precise measurements, both difficult to achieve on Venus. The analysis took 14 minutes. The results appeared on monitors. Silicon dioxide, 45%, aluminum oxide, 16%, magnesium oxide, 11%, iron oxide, 9%, calcium oxide, 7%. The numbers described a rock similar to terrestrial lucite basalt, a relatively rare volcanic rock, rich in potassium. This composition told stories. The high potassium content suggested unusual geological processes, perhaps involving different melting conditions in Venus's mantle. Compared to Earth's, the magnesium levels indicated the rock's origin in the planet's interior, brought to the surface through volcanic activity. The low water content, effectively zero, confirmed that Venus's surface rocks had formed in the absence of water, unlike most terrestrial volcanic rocks, which incorporate water into their crystal structures. While the drilling proceeded, the cameras continued photographing. Image 3, the clearest of the series, captured the largest collection of rocks in the highest detail. This would become the most analyzed photograph in the mission, the one that would generate decades of controversy. At 62 minutes, the acoustic sensor recorded sounds. On Earth, sound travels through air at about 340 meters per second and attenuates over distance, depending on atmospheric conditions. On Venus, with an atmosphere 65 times denser than Earth's at sea level, sound traveled more slowly, but could carry farther in certain frequency ranges. What the sensor recorded wasn't wind. At the surface, wind speeds measured less than 1 meter per second, barely perceptible. It wasn't mechanical noise from the lander's systems. That had been characterized during testing and subtracted from the recordings. What remained were irregular acoustic events, brief pulses of sound that might indicate geological activity, rocks settling, gases escaping from subsurface voids, thermal expansion cracking surface materials, or something else. The patterns didn't match typical seismic signatures. They weren't periodic, like electromagnetic interference. They weren't random, like atmospheric noise. They occurred in clusters, separated by silence, then more clusters, with different characteristics. The acoustic team would spend years analyzing these recordings, unable to definitively explain their source. At 94 minutes, the camera rotated again. To capture image 7, pointing toward the horizon. Through the atmospheric murk, barely visible, were vertical shapes, rising from the distant landscape. The resolution was insufficient to determine their nature. Mountains, escarpments, atmospheric distortions, or artifacts of the imaging process itself. 111 minutes after landing, the environmental sensors detected a change. The temperature had increased by 3 degrees. Not a measurement error, but an actual shift in the absence of wind or other obvious disturbances. What could cause such a change? Thermal cycling seemed the most likely explanation. Venus's surface receives solar radiation, even through the thick clouds, and that radiation heats the ground. Over the course of a Venusian day, 117 Earth days long, temperatures would vary slightly as the sun's position changed. But 3 degrees and 11 minutes seemed rapid for such a gradual process. The alternative explanations were speculative: subsurface heat transfer, chemical reactions releasing energy, redistribution of atmospheric gases with different thermal properties, or, though no one wanted to say it aloud, movement of materials that had been blocking or reflecting radiation differently. At 127 minutes, Venera 13 went silent. The final telemetry showed all systems still functioning, but with temperatures approaching 500 degrees at various locations within the spacecraft. The electronics had endured longer than designed, protected by refrigeration systems and insulation, but the extreme environment was winning. Components were failing, connections breaking, sensors drifting out of calibration. The last data packet transmitted included environmental readings. Temperature, 478 degrees. Pressure, 92.1 bar. Carbon dioxide concentration, 96.5%. And a final photograph. Image 8, showing the same landscape that images 1 through 7 had revealed. Rocks under an orange sky. Geology at the limits of survival. Then nothing. The silence that filled the control room was different now. Not concentration, but completion. They had succeeded. 127 minutes on the surface of Venus. 8 photographs, detailed chemical analysis, acoustic recordings, environmental data. It was more than any previous mission had achieved. It was, by the standards of the Venera program, a triumph. But as the engineers celebrated and the scientists began preliminary analysis, a few observers were already noticing something. Something subtle in the photographs. Small details that would take weeks to emerge fully, but were visible even in the first rapid examination. Patterns in the rock distributions, regularities in their sizes and shapes, arrangements that seemed less random than expected. Dr. Leonid Xanfomaliti was among the first to notice. He didn't mention it during the celebration. Scientific caution demanded he verify his observations, examine them from multiple angles, consider all prosaic explanations before suggesting anything unusual. But he saw what he saw. Rocks that appeared organized, in ways random geological processes shouldn't produce. He would spend months analyzing the images, measuring angles, calculating statistical distributions, comparing the Venera 13 landing site to terrestrial volcanic regions. The more he looked, the more convinced he became that something in those photographs didn't fit standard geological models. And then he noticed the movement. Between image 1 and image 2, taken 21 minutes apart, several objects had changed position. Not dramatically. Shifts of a few centimeters. Barely perceptible. But the camera calibration data showed no evidence of lander movement. The objects themselves appeared to have moved. Xanfomality didn't publish his findings immediately. He knew what happened to scientists who claimed to see patterns in ambiguous data. Percival Lowell's Martian canals had become a cautionary tale for the entire field, making extraordinary claims about Venus, based on low-resolution photographs, would be career-ending, without overwhelming evidence. But he couldn't dismiss what he was seeing. The patterns were there. The apparent movement was there. And no conventional explanation seemed adequate. He shared his observations with trusted colleagues. Carefully, some saw the same features. Others remained skeptical. The debate that would consume decades began quietly, in offices and laboratories, among scientists who understood both the importance of the observations and the dangers of overinterpretation. Meanwhile, the data from Venera 13 was being analyzed in every possible way. The chemical composition suggested volcanic rocks, formed in the absence of water. The temperature and pressure confirmed previous measurements, cementing our understanding of Venus's extreme surface environment. The photographs showed a landscape that was geologically young, perhaps only a few 100 million years old, suggesting ongoing volcanic activity. But geology was only part of what Venera 13 had documented. The spacecraft had visited an alien world and survived just long enough to send back a message. Whether that message contained information beyond basic geological and environmental data, whether it hinted at processes occurring on Venus that didn't fit into our existing frameworks, remained uncertain. What was certain was that 127 minutes on Venus's surface had generated questions. Questions that 4 decades later remained unanswered. The photographs showed something. The sensors detected something. The question was whether that something was extraordinary or ordinary, whether we were seeing the limits of Venus's extreme geology, or the hints of something more complex. The answer couldn't come from further analysis of the Venera 13 data. That information had been extracted, examined, debated, scrutinized. Every pixel of every photograph had been analyzed. Every measurement had been calibrated and recalibrated. Every signal had been processed and reprocessed. The answer could only come from returning to Venus, from landing again, from seeing if other sites showed similar features. And that return would take not months or years, but decades. Decades during which Venus rotated slowly beneath its clouds, its surface hidden from telescopes, its mysteries preserved in an environment too hostile for casual investigation. Venera 13 had opened a window onto Venus for 127 minutes. That window had closed, and the question of what lay beyond it, what was actually happening on Venus's surface, in Venus's atmosphere, in Venus's strange and extreme environment, remained open. The scientists who had watched Venera 13's data arrive knew they had documented something significant. Whether that significance was geological, atmospheric, or something else entirely, would require more missions, more data, more time. But time was something Venus had in abundance. The planet would wait, patient and hostile, for humans to return and look again at the rocks under the orange sky, to measure again the temperatures and pressures that destroyed everything we sent, to listen again to the sounds that might be geology, or might be something else. The photographs from Venera 13 showed what they showed, and what they showed was enough to keep scientists arguing for 40 years about what they were actually seeing. about whether Venus was dead or dynamic, about whether the patterns meant something or nothing. 127 minutes, 8 photographs, a chemical analysis, environmental readings, acoustic recordings, and questions. So many questions. The Soviet Union would send 2 more landers to Venus. Venera 14, just 4 days after Venera 13, landing 2,000 kilometers away, and surviving 57 minutes, and Venera 15 and 16, orbiters that mapped the planet with radar in 1983 and 1984. After that, the Venera program ended. The Soviet Union would collapse 7 years later. The institutional knowledge, the engineering expertise, the accumulated wisdom of landing on Venus, all of it would be dispersed, lost, or forgotten. And Venera 13's photographs would remain, frozen in time, showing rocks on an alien world in 127 minutes of observation. That captured either something ordinary or something extraordinary, depending on who was looking and what they were willing to see. The scientists who believed the photographs showed something unusual: organized arrangements, possible movement, patterns inconsistent with random geology, faced a problem. They couldn't prove it. The evidence was suggestive, but not conclusive. Extraordinary claims required extraordinary evidence, and what they had was ambiguous evidence that could be interpreted multiple ways. The scientists who believed the photographs showed nothing unusual, ordinary rocks distributed by ordinary geological processes, faced a different problem. They couldn't definitively prove that either. Venus's geology operated in such extreme conditions that many processes were poorly understood. Saying this is normal for Venus required understanding what normal meant. For a planet we'd visited only a handful of times, both sides were working from profound ignorance, filling gaps in knowledge with interpretation, seeing patterns or randomness, depending on their prior assumptions about what Venus should look like. And Venus itself offered no clarification. The planet rotated slowly through space, its surface hidden beneath permanent clouds, its secrets preserved in an environment that destroyed everything we sent to investigate. The rocks that Venera 13 photographed remained where they were. If they were still rocks, if they were still there, if they had been what we thought in the first place. 40 years would pass, 4 decades during which planetary science advanced dramatically, during which we sent multiple rovers to Mars, orbited the outer planets, landed on Titan, flew past Pluto. 4 decades during which our understanding of extreme environments and exotic chemistry expanded enormously, during which we discovered thousands of exoplanets and began seriously discussing the possibility of life beyond Earth. But Venus remained neglected, its mysteries unresolved, its secrets intact. The planet we'd visited most frequently in the early space age became the planet we ignored. In the later space age, dismissed as too hostile, too expensive, too unlikely to yield interesting results. The photographs from Venera 13 sat in archives, occasionally examined by researchers, but largely forgotten by the broader scientific community. The mission that had achieved 127 minutes of survival on the most hostile surface in the solar system became a historical footnote, overshadowed by more recent achievements on more accessible worlds. But the questions persisted among a small community of scientists who specialized in Venus, who studied its geology and atmosphere and evolution, who looked at the Venera data with fresh eyes and modern analytical tools. The questions refused to disappear. What did Venera 13 actually photograph? What processes were occurring on Venus's surface? What was causing the patterns some observers saw in the images? What had moved between photographs? If anything actually moved? These questions had no consensus answers. And without new missions to Venus, without new data to compare against the Venera observations, the questions would remain unanswerable, provocative enough to generate speculation, ambiguous enough to prevent conclusions. This was the state of knowledge when, in 2020, researchers announced the detection of phosphine in Venus's atmosphere. That discovery would reignite interest in Venus, would catalyze new mission proposals, would remind the planetary science community that Earth's sister planet remained deeply mysterious, despite decades of exploration. But that renaissance of Venus science would come too late. For the scientists who had worked on Venera 13, who had watched the telemetry arrive in real time, who had seen the first photographs of Venus in color, most of them would not live to see humanity return to Venus, would not witness resolution of the mysteries they had helped uncover. Xanfomalidi died in 2022, still convinced that the Venera photographs showed something extraordinary, but uncertain what that something was. His publications on the subject remained controversial, cited by some as important observations, and dismissed by others as pattern recognition run amok. The truth, whatever it was, remained on Venus, waiting beneath the clouds, beneath the orange sky, in conditions that melted lead and crushed spacecraft and dissolved questions in ambiguity. 127 minutes had not been enough. 8 photographs had not been enough. 1 chemical analysis had not been enough. The mystery endured, and would continue to endure, until someone returned to Venus and looked again. More carefully this time, with instruments designed not just to survive, but to see clearly, to measure precisely, to distinguish between geology and something else. But that return required will, funding, technology, and commitment. It required believing that Venus's mysteries were worth solving, that the ambiguous patterns in decades-old photographs justified billions of dollars in new missions. And that belief in the risk-averse culture of modern space exploration was harder to generate than the missions themselves would be to execute. So Venus waited, patient as only a world can be patient. The rocks sat under the orange sky. If they were rocks, if they sat, if the orange sky still looked the same after 40 years of rotation, beneath clouds that never parted, and the photographs from Venera 13 remained, showing 127 minutes of observation. That captured either everything important about Venus or nothing important at all, depending on what you believed about patterns and randomness, and the possibility of organization in the most hostile environment humanity had ever visited. The photograph hangs on a wall in the Vernadsky Institute in Moscow, printed large enough to see the grain, the scan lines, the orange tint that makes Venus's surface look almost welcoming. Until you remember what those colors represent, visitors sometimes stop to look at it. This image from another world, taken 40 years ago by a machine that survived barely longer than a feature film. Most don't realize what they're looking at. They see rocks. They see a barren landscape. They see confirmation that Venus is exactly what they've been told it is. A dead world, a cautionary tale, Earth's evil twin. But occasionally someone looks longer, studies the arrangements, notices the patterns, and they ask the question that has no good answer. What is that? The woman who maintains the Institute's archive of Venera data is 73 now, one of the last direct links to the Soviet Venus program. She was 29 when Venera 13 landed, a junior data analyst who spent months processing telemetry. She remembers the excitement, the sense that they were accomplishing something unprecedented, landing on Venus repeatedly, while the Americans focused on Mars. "We thought we were documenting a dead world," she says in Russian, gesturing at the photograph. "But the longer you look at these images, the less certain you become. Not because you see life. I'm not claiming that. But because you realize how little we understood about what we were seeing. Venus doesn't fit our categories. It never has." She pulls up digital files on a decades-old computer, images that have been scanned and rescanned as formats changed and storage media evolved. The original magnetic tapes are degrading. Despite climate-controlled storage, in another decade, they might be unreadable. When that happens, humanity will lose the raw data, the actual signals sent from Venus, before processing and interpretation altered them. "This is what haunts me," she continues. "We went to Venus 6 times with landers. 6 times we touched the surface and transmitted data, and then we stopped. For 40 years. Nothing. Imagine if we'd explored Earth that way. Sent 6 expeditions to random locations, survived a few hours at each, then never returned. What would we know? What would we miss?" The answer is obvious. We'd miss everything that makes Earth interesting. The diversity of geology, the variations in chemistry, the complexity that emerges from billions of years of planetary evolution. 6 data points don't describe a world. They barely hint at its nature. Venus received those 6 data points, and then silence. The planet rotated beneath its clouds, its surface hidden from telescopes, its processes continuing, whatever those processes were, without observation. 40 years is nothing in geological time, but everything in human institutional memory. The engineers who built Venera retired, or died. The scientists who analyzed the data moved to other fields, or passed away. The knowledge of how to land on Venus, the practical, hard-won understanding of what works and what fails, dispersed and faded. Dr. James Cutts worked at NASA's Jet Propulsion Laboratory for 45 years, before retiring in 2020. He spent much of that career trying to convince colleagues that Venus deserved attention. The arguments he made were sound. Venus is closer than Mars, making missions shorter and cheaper. Venus offers insights into planetary climate evolution, directly relevant to Earth's future. Venus might host life in its cloud layers, where temperatures and pressures are benign. None of it mattered. Mars dominated funding. The Moon received renewed interest. Venus remained a secondary target, interesting in theory, but not compelling in practice. The problem, Cutts explains, is that Venus requires different technology than Mars or the Moon. Mars is cold and dry. You can use commercial electronics with minimal modification. Venus is hot and corrosive. You need custom components that can survive extreme conditions. That development is expensive. And mission planners don't want to invest in technology for one planet when they can use off-the-shelf components for another. The result was stagnation. Between 1984 and 2020, not a single spacecraft landed on Venus. The Magellan orbiter mapped the surface with radar from 1990 to 1994. providing invaluable data. The European Space Agency's Venus Express orbited from 2006 to 2014, studying the atmosphere, but no mission returned to the surface, where Venera 13 had photographed those ambiguous rocks. Without new surface data, the questions the Venera missions raised couldn't be resolved. Scientists argued about interpretation, whether patterns in photographs were meaningful, or artifacts, whether apparent movement was real, or instrumental error. But arguments aren't discoveries. The mystery calcified, becoming one of those persistent but low-priority puzzles that space science accumulates. Interesting enough to mention, not important enough to fund. Then came phosphine. The announcement in September 2020 that researchers had detected phosphine in Venus's atmosphere wasn't supposed to change everything. It was a single observation, tentative and controversial, of a molecule that shouldn't exist, in significant quantities, under Venusian conditions. But phosphine has peculiar chemistry. On Earth, it's produced primarily by anaerobic bacteria, by industrial processes, or by decomposition of organic matter. On Venus, none of these sources should exist. The detection sparked immediate debate. Other scientists reanalyzed the data, reaching different conclusions. Some confirmed the findings. Others claimed the signals were misidentified. Additional observations yielded conflicting results. Papers were published, critiqued, revised. The scientific process worked exactly as designed, slowly, carefully, incorporating new evidence and rejecting weak claims. But the phosphine controversy accomplished something unexpected. It made Venus interesting again, not to specialists, who had never stopped finding Venus interesting, but to the broader scientific community and to funding agencies. Suddenly, mission proposals that had languished for years received serious consideration. The planet we'd ignored for 4 decades became a priority. NASA announced Da Vinci, Deep Atmosphere Venus, investigation of noble gases, chemistry, and imaging. Launch window in the early 2030s. Arrival approximately 2 years later. The mission would drop a probe through Venus's atmosphere, analyzing composition in unprecedented detail. It wouldn't land, but during the final kilometers of descent, it would photograph the surface. With resolution 100 times better than Venera achieved, the European Space Agency committed to Envision, an orbiter designed to map Venus, with radar resolution down to 10 meters, and spectrometers capable of determining surface mineralogy. Launch scheduled for the early 2030s. The mission would search for active volcanism, measure outgassing, track changes over time. India's space agency proposed Shukrayan-1, an orbiter focused on atmospheric chemistry and surface studies. Russia discussed reviving the Venera program with Venera D, a modern lander equipped with instruments that could survive hours or even days. On the surface, neither mission received firm funding, but both remained under consideration. After 40 years of neglect, Venus suddenly had 4 proposed missions from 3 space agencies. The Aussie Renaissance of Venus exploration was beginning. But these missions faced a fundamental problem. They weren't designed to answer the questions Venera 13 raised. Da Vinci wouldn't land. It would photograph the surface during descent, but be destroyed on impact. Envision would orbit. It would map globally, but couldn't examine details at the scale of individual rocks. Shukrayan-1 and Venera D might provide new data, but their capabilities remained uncertain. None of the confirmed missions would return to the Venera 13 landing site. None would examine the specific rocks that had generated controversy. None could determine definitively whether those rocks showed patterns, indicative of organization, or merely represented ordinary Venusian geology. Dr. Martha Gilmore, planetary geologist at Wesleyan University, has been advocating for a Venus rover for over a decade. Not an orbiter, not a brief-lived lander, but a mobile platform capable of exploring multiple sites and surviving long enough to observe changes over time. We need persistence, Gilmore emphasizes. Mars rovers have operated for years, even decades. They've transformed our understanding of Mars by going beyond single landing sites, by examining how different locations relate to each other. Venus deserves the same approach. The technical challenges are formidable. A Venus rover would need wheels that function at 475 degrees Celsius, motors that don't seize under crushing pressure, electronics that survive in corrosive atmosphere. The Soviet landers used refrigeration systems to keep internal temperatures below critical limits. But refrigeration requires energy, and energy is limited. A rover would need to move, which requires more power than a stationary lander. How do you generate that power on Venus? Solar panels don't work well. Only 5% of incident sunlight reaches the surface. Nuclear power sources could work, but add cost and political complications. Some engineers have proposed mechanical energy storage, wind-up springs that could power brief periods of activity. Others suggest using Venus's thermal energy itself, creating heat engines that operate on temperature differentials between the hot surface and slightly cooler subsurface. These are solvable problems, given sufficient funding and development time. But sufficient funding means billions of dollars, and development time means decades. A Venus rover capable of addressing the Venera mysteries wouldn't launch until the 2040s at the earliest, wouldn't arrive until the mid-2040s, wouldn't return data until 60-plus years after Venera 13 took those 8 photographs. By then, everyone who worked on the Soviet Venus program will be dead. The institutional memory will be completely gone. The mysteries will persist, not because they're unsolvable, but because we waited too long to pursue solutions. Dr. David Grinspoon sits in his office in Colorado, surrounded by books about Venus and images from various missions. He's written extensively about the planet, arguing for decades that Venus deserves more attention. The phosphine detection vindicated his advocacy, but he takes no satisfaction from it. We should have been doing this all along, he says. Venus is the most Earth-like planet in the solar system. Similar size, similar composition, similar distance from the Sun. Understanding why Venus evolved so differently from Earth is crucial to understanding planetary habitability. But we neglected it for 40 years because Mars seemed more accessible and the Moon had political momentum. He pulls up the Venera 13 photographs on his computer, images he's examined countless times. These show us something important, even if we can't agree on what. They show us the limits of brief observations in extreme environments. We looked at Venus for 127 minutes and thought we understood what we were seeing. But did we? Can you understand anything from 127 minutes of observation? The question is rhetorical, but it highlights the epistemological problem at the heart of Venus exploration, when environments are so different from Earth that our intuitions fail, when observations are so brief. That context is missing. When instrumentation is pushed to operational limits, in hostile conditions, how do we distinguish signal from noise, meaning from artifact, extraordinary from ordinary. Science demands reproducibility. An observation made once needs to be confirmed by independent measurements. But Venus hasn't allowed reproducibility. The Venera 13 landing site hasn't been revisited. The phenomena the lander might have detected, patterns in rock distribution, apparent movement of objects, unusual acoustic signals, haven't been observed again, because no mission has returned to look. This violates the fundamental requirement of scientific verification. Without repetition, observations remain provisional, suggestive, but not conclusive. The Venera 13 data exists in a liminal space, too significant to dismiss, but too ambiguous to confirm, pointing toward possibilities that can't be verified. Without investments no one is willing to make, the upcoming missions will help, but incompletely. Da Vinci's high-resolution photographs will show whether other regions of Venus display similar features to those Venera captured. If they do, that suggests planet-wide geological processes rather than localized anomalies. If they don't, that either means the Venera observations were artifacts, or that whatever created those patterns exists only in certain locations. Envision's radar mapping will reveal whether Venus's surface changes over time. At scales we can detect, volcanic activity should be obvious, new lava flows, altered topography, fresh thermal emissions, but subtler changes, rocks shifting position, surface textures altering, distributions of materials reorganizing, might be invisible to orbital radar. What's needed is the one thing these missions can't provide: sustained surface observations, days or weeks of continuous monitoring, watching how Venus behaves. When you observe it for longer than the brief windows the Venera landers provided, do things change? Do patterns emerge over time? Do the phenomena that appeared in Venera photographs represent snapshots of dynamic processes, or were they static features that only seemed to change due to instrumental effects? These questions can't be answered from orbit, or by cameras falling through the atmosphere. They require presence, machines on the surface, surviving long enough to see beyond initial conditions, equipped with instruments specifically designed to detect organization, complexity, change. Dr. Kevin Hand, an astrobiologist at NASA's Jet Propulsion Laboratory, studies how to search for life in extreme environments. His primary focus is Europa, Jupiter's ice-covered moon with a subsurface, ocean. But the principles apply anywhere. How do you recognize life when it might be radically different from anything you've encountered? We tend to look for Earth-like biosignatures, Hand explains. Organic molecules, particular isotopic ratios, gases that indicate metabolism. But these are signatures of Earth life. If Venusian life exists, if anything complex is happening there that we'd want to call alive, it might not produce any of those signatures. He describes alternative approaches, looking for complexity itself, rather than specific molecules. Information theory provides tools for quantifying how organized a system is, how far it deviates from randomness. Chemical networks can be analyzed for patterns that suggest autocatalysis or other self-sustaining processes. Physical arrangements can be tested statistically to determine if they're more ordered than geological processes alone should produce. The problem, Hand continues, is that these approaches require data we don't have from Venus. We need detailed compositional analysis of multiple samples. We need time series observations showing how things change. We need spatial distributions at fine scales. The Venera missions provided snapshots. We need video. The metaphor is apt. 8 photographs from Venera 13 show 8 moments frozen in time. They reveal what Venus looked like at those specific instants, but nothing about what came before or after. Movement between frames might indicate dynamic processes, or might be instrumental artifacts. There's no way to distinguish without more temporal resolution. This is why the debate about Venera 13 has persisted for 40 years without resolution. The data is insufficient to prove any interpretation definitively. Both sides, those who see something unusual in the photographs and those who see only ordinary geology, are extrapolating from inadequate information, filling gaps with assumptions based on what they expect Venus to be like. The truth is simpler and more frustrating. We don't know what Venera 13 photographed because we don't know Venus well enough to recognize what's ordinary there. When the ordinary is unknown, identifying the extraordinary becomes impossible. Dr. Sue Smrekar, Deputy Principal Investigator for the Veritas Mission Concept, Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy, has spent years developing technologies for Venus exploration. Veritas was selected by NASA, then delayed indefinitely due to budget constraints, then reselected, then delayed again. The cycle of promise and disappointment has defined Venus mission planning for decades. The frustrating thing, Smrekar says, is that we have the technology. We know how to build spacecraft that can survive on Venus. The Soviets proved that in the 1970s and 80s. We've improved on their designs, better electronics, better materials, better thermal management. We could land on Venus today and operate for hours, maybe days, but we don't, because funding priorities lie elsewhere. She pulls up technical diagrams showing proposed Venus landers with advanced capabilities, ground-penetrating radar, to examine subsurface structure, drilling systems that can collect samples from multiple depths, spectrometers capable of detailed mineralogical analysis, cameras with resolution high enough to see millimeter-scale features. With these instruments, Smrekar explains, we could answer the questions Venera raised. We could examine those rock formations in detail, determine if they're ordinary basalt or something unusual. We could watch the surface over days, see if anything moves or changes. We could analyze the acoustic environment, determine if those sounds Venera detected were geological or something else. But these capabilities remain hypothetical. Veritas, if it finally launches, will be an orbiter, not a lander. Its radar will map Venus globally with 15-meter resolution. Revolutionary compared to previous missions, but insufficient to see individual rocks. The mission will answer important questions about Venus's geological history and current activity, but it won't resolve the mysteries the Venera photographs present. That resolution requires missions that don't yet exist, technologies that haven't been funded, commitments that haven't been made, and time is running out, not for Venus, which will wait indefinitely, but for the opportunity to learn from people who worked on the original Venera program. The Russian Academy of Sciences maintains an archive of Venera documents, engineering specifications, mission logs, analysis reports, personal notes from scientists. Much of it has been digitized, but the digitization process itself involves interpretation. Someone must decide what's important enough to preserve, how to organize information, what context to provide. When that someone didn't work on the missions directly, crucial nuance can be lost. There's a particular type of knowledge that exists only in the minds of people who actually built and operated complex systems. It's not written in manuals or documented in reports. It's the accumulated understanding of how things really work versus how they're supposed to work. The subtle tricks and workarounds that make missions succeed. The hard-won intuitions about what matters and what doesn't. This knowledge is dying. The youngest engineer who worked on Venera 13 is now in his 70s. The scientists who analyze the data are mostly gone. Within another decade, there will be no one left who remembers the actual missions, who can look at the photographs and recall the discussions they generated when fresh, who knows what questions were asked and why some were pursued, while others were set aside. When they're gone, the data will remain, but its context will be lost. Future researchers will have the photographs, the telemetry, the published papers, but they won't have the unwritten understanding, the institutional memory, the lived experience of people who were there. When Venus revealed itself for 127 minutes and sent back messages we're still trying to interpret, Dr. Rakesh Moghul at California State Polytechnic University has spent years reanalyzing Venera data. With modern computational tools, machine learning algorithms can identify patterns humans might miss. Statistical methods developed for other fields can be applied to planetary science. The raw data contains more information than 1980s analysis techniques could extract. We're finding things, Moghul says carefully. Not dramatic findings, not proof of anything extraordinary, but subtle patterns in the data that weren't apparent in the original analysis. Temperature variations that correlate with surface features, chemical signatures that suggest more complex processes than simple volcanic rock formation, acoustic signals with structure that doesn't match known geological sources. He emphasizes that these findings don't prove anything about life or even unusual geology. They demonstrate only that the Venera data contains more complexity than was initially recognized, whether that complexity reflects Venus's unusual environment, instrumental artifacts, or something genuinely anomalous remains uncertain. The honest answer, Moghul admits, is that we need more data, not better analysis of old data. We've extracted everything we can from those 8 photographs and few hours of measurements. We need new observations from new locations with better instruments. Until we have that, we're arguing about interpretation of insufficient information. This is the consensus among researchers who study Venus. The existing data has been exhausted. Every reasonable analysis has been performed. The photographs have been examined, pixel by pixel. The chemical compositions have been compared to terrestrial rocks and theoretical models. The acoustic signals have been processed with every available technique. What remains are questions that can't be answered. With the data we have, are the patterns in rock distribution significant? Did objects actually move between photographs? What caused the acoustic signals Venera detected? Are there processes occurring on Venus's surface that don't fit into standard geological categories? These questions will persist until new missions provide new data, and new data will come. Da Vinci will launch in the early 2030s, and Vision shortly after. They'll revolutionize our understanding of Venus's atmosphere and global geology. but they won't visit the Venera 13 landing site, won't examine those specific rocks, won't settle the debate that has consumed 4 decades. That settlement requires a dedicated surface mission, returning to the places Venera explored, equipped to observe what Venera could only glimpse. Such a mission is technically feasible and scientifically justified, but it's not funded, not planned, not scheduled. It exists in conceptual space, discussed at workshops, and proposed in white papers, but never advancing to actual development. The question is why? Why, when we have the capability and the scientific motivation, don't we return to Venus's surface and resolve these mysteries? Dr. Lindy Elkins Tanton, planetary scientist and director of Arizona State University's School of Earth and Space Exploration, offers a blunt assessment. Venus doesn't fit our narrative about solar system exploration. We want to find life on Mars, or Europa, or Enceladus, places where we can imagine Earth like biochemistry. Venus is too hot, too hostile, too different. It challenges our assumptions about what's possible and what's worth investigating, so we avoid it. She argues that this avoidance reflects a broader failure of imagination. In astrobiology, we're searching for life as we know it, in environments we consider habitable by Earth standards, but the universe is larger than our experience. Chemistry is richer than our current understanding. If we only look for familiar patterns, we'll miss everything that's genuinely alien. Venus, in this view, represents a test of our willingness to confront genuine alienness. The planet isn't Earth-like. Despite surface similarities, it's profoundly different. Different temperature regime, different atmospheric chemistry, different geological processes. If something complex exists there, it won't be cells with membranes and DNA. It will be something we have no category for, no framework to understand. And that's precisely why Venus matters. Not because it definitely hosts life, but because it forces us to expand our conception of what's possible. The Venera photographs show rocks that might be arranged in patterns, or might not. The patterns might indicate organization, or might reflect unusual geology. The organization might be life, or might be complex chemistry. These ambiguities aren't failures of observation. They're features of reality. When you explore environments radically different from Earth, Venus is teaching us that recognizing the extraordinary requires first understanding the ordinary. And understanding the ordinary requires sustained observation, not brief glimpses. The upcoming missions will provide new glimpses. Longer, clearer, more detailed, but glimpses nonetheless. Venus deserves more. The planet that should have been Earth's twin, but became something else entirely. The world that represents our greatest planetary climate mystery. The surface that might host processes we don't have names for. This deserves sustained attention. Whether it will receive that attention remains uncertain. Space exploration operates on timescales of decades, driven by funding cycles and political priorities that shift unpredictably. Venus has advocates, but so does Mars, the Moon, the outer solar system, exoplanet science. Resources are limited. Choices must be made, and so Venus waits. The planet rotates slowly, one rotation every 243 Earth days, retrograde, slower than its orbital period. The surface remains hidden, beneath permanent clouds. The rocks that Venera 13 photographed sit where they sat 40 years ago. If they're still there, if they were rocks, if they haven't been covered by volcanic ash, or moved by processes we don't understand. The photographs remain too. Digital files on servers, printed images in archives, data that has been analyzed and reanalyzed until every pixel is familiar. They show what they show, neither more nor less. The question is what that is. Dr. Sanfomaliti, before he died, spent his final years reviewing the Venera data. One last time. He published a series of papers, each more speculative than the last, suggesting that Venus might host something, organized enough to deserve investigation, but not organized enough to call alive by any standard definition. His colleagues were divided. Some respected his careful documentation of anomalies. Others dismissed his work as the pattern recognition of an aging scientist, seeing what he wanted to see. Both reactions missed the essential point. Sanfomaliti was asking a question, not claiming an answer. The question was simple. Have we looked carefully enough at Venus to know what's ordinary there? And if we haven't, how can we possibly identify what's extraordinary? This question survives him. It survives the Soviet Union that funded the missions he analyzed. It survives the Cold War context in which Venus exploration began. It remains relevant because Venus remains mysterious, because our ignorance about the planet is profound, because 40 years of neglect have left questions unanswered that should have been resolved decades ago. In Moscow, the archive photograph hangs on the wall. Rocks under an orange sky. 127 minutes of observation, frozen forever, showing either everything important or nothing important, depending on what you believe about patterns and possibility. Visitors still stop occasionally to look. Most move on quickly, satisfied they've seen what there is to see. But some linger, studying the arrangements, noticing details, asking questions. And the woman who maintains the archive, who was there when the data arrived, who has spent 40 years with these images, tells them what she tells everyone. We went to Venus and brought back postcards, beautiful, mysterious postcards from an alien world. But postcards aren't the same as being there. Postcards show you moments, not stories. To understand Venus, we need to return. Stay longer. Look more carefully. Be willing to see what's actually there, instead of what we expect. She's 73 now. She won't live to see humanity return to Venus's surface. Neither will most of the scientists who have spent careers advocating for Venus missions. They'll die with the mystery unresolved, their questions unanswered, their work incomplete. But the questions will persist. They're embedded in the data now, in those 8 photographs, and few hours of measurements. Future scientists will examine the Venera images and notice the same patterns, wonder about the same possibilities, face the same frustrating lack of resolution, and eventually, perhaps decades from now, someone will fund a mission that returns to Venus, not to map it or measure it from orbit, but to land, to stay, to observe carefully over time. They'll build a lander that survives days or weeks. They'll send a rover that can explore multiple sites. They'll equip it with instruments designed not just to measure chemistry and temperature, but to detect complexity, organization, change. And then finally, we'll know. Not everything about Venus. One world can't be understood by any single mission, but more than we know now. Enough to determine if the patterns in the Venera photographs were meaningful. Enough to settle whether something dynamic is occurring on Venus's surface. Enough to answer the question that has haunted planetary science. for 40 years. What did the Soviets find on Venus? Until that happens, the mystery endures. The photographs remain, and Venus rotates slowly beneath its clouds, keeping secrets we glimpsed once for 127 minutes, but never saw clearly enough to understand. The cosmos is patient. Venus is patient. The rocks under the orange sky. If they're still rocks, if they're still there, if they still matter, wait for someone to return and look again. Not soon, not as soon as they should, but eventually. Because mysteries don't disappear. Just because we ignore them, they persist, embedded in data, preserved in photographs, waiting for the moment when humanity decides that understanding matters more than convenience, that solving mysteries justifies the cost, that Venus deserves the attention we've given Mars, and the Moon, and everywhere else we've explored, while neglecting Earth's closest neighbor. That moment will come. It must come. The questions are too important, the implications too significant, the mysteries too compelling, to remain forever unresolved. But for now, Venus waits, and the photographs from Venera 13 remain, showing 127 minutes of observation. That might have captured something extraordinary, or nothing at all, and we still don't know which.